detect that there's too much acid in the blood. They're going to be picking up the level of chemicals in the blood, hence the word chemoreceptor. And they're going to say, look, there's too much CO2 in the blood. We need to send a signal to try and fix this. What are they going to do at that point? They'll send a signal to the respiratory centers to increase ventilation. And that increase in ventilation is going to help blow off the CO2. Again, CO2 is an acid. So blowing off excess CO2 is going to help rectify that acidotic state. Okay? So that increase in ventilation will then decrease the amount of plasma CO2. The plasma pH will rise again back to neutral, right? Not acidic, but neutral at this point. And that will turn off the initial signal. Okay? Any questions on this flow chart? Any questions on that scenario? Okay.
So CO2 makes it more acidic?
Correct.
Okay.
It's a biological acid, right? Okay. So we're going to go through similar scenarios to that scenario, but looking at different compensation and different types of disturbances. All right. Let's talk about the renal compensation. So this is the third line of defense. This takes a much longer time. Okay, the kidney, the lungs can get a signal to increase ventilation at a much quicker rate, but the signal to go to the kidneys takes hours or even days. So this is a much more delayed response. All right, let's say we have a situation where, again, we have an acid-base disturbance that's starting in the lungs, and the signal is sent for the kidneys to compensate. We can either regulate the amount of hydrogens that are secreted, right? We can either increase or decrease the hydrogen ion that's secreted into the urine, or we can increase or decrease the amount of bicarbonate that's reabsorbed. Okay, we can also regulate the synthesis of new bicarbonate in the renal tubules. We'll talk about that pathway. But basically, the kidneys will chime in to help correct that acid-base disturbance that started in the lungs. So the effects of increased acidity will increase the amount of hydrogen ions that are secreted. Again, if you have an acidic state, you want to lose hydrogen ions. You will increase the reabsorption of bicarbonate. Again, if you have an acidic state, you want to hold on to bicarbonate, so you're going to increase the rate of reabsorption, and you're going to increase the rate of new bicarbonate synthesis, which happens in the renal tubules. All righty? All right. Let's talk about the two areas of the kidney tubules where we regulate the secretion and the absorption of bicarbonate and hydrogen. So the first one is going to be the proximal tubule. We talked about the proximal tubule. It's that first part of the renal tubules right after the glomerulus. Bicarbonate is going to be reabsorbed here, as well as hydrogen ion secretion. We'll talk about the mechanism in a minute. But it's important to understand in the proximal tubules, we have bicarbonate being reabsorbed into the blood and hydrogen ions being secreted out into the urine, right, into the filtrate. Under normal conditions, we have most of the filtered bicarbonate being reabsorbed. What is a condition where you would not want to reabsorb most of the bicarbonate? And again, I'm testing your understanding of this whole process. So practice trying different scenarios and talking yourself through it. What is a process? What is a state where you do not want to reabsorb most of the bicarbonate? Respiratory alkalosis. Perfect. So you have a respiratory alkalosis. You don't want to reabsorb all of that bicarbonate. That's going to work against you. What do you want to do instead? You want to pee out or secrete hydrogen ions, right? So you want to pee out or secrete hydrogen ions, right? I'm sorry, you want to reabsorb hydrogen ions and you want to pee out or secrete bicarbonate. Okay. Does that make sense? Are there any questions on that bit? Okay, when we talk about the distal tubule and the collecting duct, secretion of hydrogen ions is coupled again to new bicarbonate synthesis. So these two processes work hand in hand. So we're going to secrete hydrogen ions, lose them into the urine, as well as make new bicarbonate. Okay, and those two scenarios will help to rectify that acid-base disturbance. Now, under normal circumstances, new bicarbonate is going to be added to the plasma, meaning that's going to be reabsorbed into the blood, whereas those hydrogen ions are going to be secreted out into the tubular fluid. That's what would happen normally, unless there's some sort of compensation taking place. Right? So typically, or normally, most of the bicarbonate is reabsorbed, right? Most of the hydrogen ions are secreted in the proximal tubule, and then again, in the distal tubule and collecting ducts, there's new form bicarbonate being reabsorbed into the blood, and there are hydrogen ions being secreted out into the tubular fluid. So this is what's happening typically, normally. And so these processes can be exaggerated or negated depending on what type of acid-base disturbance you're in. All right, let's talk about some mechanisms here. So this is a proximal tubule cell, and this is a mechanism of how the carbonic acid is used to help buffer the blood. So on the left of this image, we have the lumen of the tubule. Right, so this is where our filtrate is, or our urine that's being created. And on the right here, we have the peritubular fluid, which is surrounded by the peritubular capillaries. That's where we have reabsorption back into the blood. Now, we have hydrogen and bicarbonate being freely filtered across the glomerulus, and they're going to wind up in the tubule. They're going to combine together to form this carbonic acid. So this H2CO3 is carbonic acid. All right. That will then, under the influence of carbonic anhydrase, this enzyme here on the apical membrane, are going to dissociate into water and carbon dioxide, which can freely float across the epithelial cell. Once that water and carbon dioxide are in the cell, they'll come together again under the influence of that second enzyme. So this is carbonic anhydrase 1. Carbonic anhydrase 2 is going to reconvert those two molecules, water and carbon dioxide, back into this carbonic acid. And in this carbonic acid state now, it freely dissociates into hydrogen ions, which is what it initially were. So this is a way to get these products across the epithelial cell and back into the form that they were before they were moved across the epithelia. All right, so acid and bicarbonate become carbonic acid, dissociate to water and carbon dioxide, move into the cell, reconverted to that carbonic acid, and then dissociates into acid and bicarbonate again. So what we started with in the tubular fluid, we end up with in the cell. Now at this point, two things happen. That acid can be secreted via two mechanisms, either exchanged for sodium, right? At a transporter here, exchanged for sodium. So sodium's coming in along its gradient, and that energy is used to kick hydrogen ions out. Or it can move across this proton pump. So this proton pump is using the help of ATP to pump hydrogen ions out of the cell. So these two mechanisms are responsible for hydrogen ion secretion. The second thing that happens at this point is this bicarbonate is reabsorbed into the blood. Again, two mechanisms for that. Either using the help of sodium again, or exchange for chloride. So chloride comes into the cell, and then that energy is used to allow bicarbonate to move out of the cell. Okay, any questions on this process? It's a little bit complicated.
So the hydrogens need ATP?
They don't need ATP, but that's one of the mechanisms. This is called a proton pump or hydrogen pump, and it's using ATP to pump hydrogen ions out of the cell. That's one mechanism, right? That's active transport. The second mechanism is secondary active transport, where we use the chemical gradient of another ion, in this case sodium, to generate energy to move potassium down this gradient. Hydrogen down this gradient, sorry.
So hydrogen will be greater in the tubular fluid than inside the cell.
Hydrogen will be greater in the tubular fluid than inside the cell, that's correct. Okay, so we have to actively pump it out because there's not a gradient there. Any other questions here? All right, so I'll go over this one more time. We have that acid and that bicarbonate freely filtered across the glomerulus. They combine to form carbonic acid, H2CO3. That carbonic acid, under the influence of carbonic anhydrase 1, that first enzyme on the epithelial apical membrane, becomes water and carbon dioxide. Those are now free to move into the epithelial cell, right? In the absence of any type of health. The carbon dioxide and the water, once inside the cell, will reconvert into that carbonic acid again under the influence of the second carbonic anhydrase enzyme. This carbonic acid now freely dissociates into hydrogen ions and bicarbonate. Remember, these are what we started with in the tubular fluid. And then that acid can be secreted into the urine, and that bicarb can be reabsorbed into the blood. All right, let's keep moving. Let's talk about the distal tubule and the collecting duct here. So this gets a little bit more complicated. We bring in the phosphoric acid. So we have hydrogen ion, very similar process. We have hydrogen ions and this hydrogen phosphate here, and that combines to give us phosphoric acid. That can move into the cell, and then once in the cell, it's going to be in the form of carbon dioxide and water again. That carbon dioxide and water reconvert using the help of carbonic anhydrase into bicarbonate, into carbonic acid, and that carbonic acid once again dissociates with hydrogen ions and bicarbonate. Bicarbonate can be reabsorbed into the blood. It can be exchanged for chloride, or, right, so that bicarbonate can be reabsorbed into the blood, being exchanged for chloride. And then the second process happening here is the hydrogen ions are being secreted. Now, hydrogen ions, again, can be exchanged for potassium or pumped out using that proton pump, that hydrogen pump. Okay, so very similar process to what we saw at the proximal tubule. The big picture here is that acid is secreted and bicarbonate is reabsorbed. So all this fancy acids, they're just helping these molecules get across the membrane and keeping them in a certain state. The big picture is acid is going to be reabsorbed in the tubular fluid, bicarbonate is reabsorbed into the blood. Okay, and that can be regulated. That can be regulated depending on the acid-base state of the body. Let's talk briefly about glutamine in this compensation. So glutamine has an effect that's similar to acidosis, right? And it helps to generate new bicarbonate and secrete hydrogen ions. So it can help the kidneys in its role of regulating the acid-base compensation, okay? So if we look at glutamine, right, once it's in the epithelial cell, it does the same thing that we talked about. It dissociates into bicarbonate, which can be reabsorbed into the blood, and then this acid in the form of ammonium this time. So this ammonium is excreted into the urine, and that ammonium actually has 4 hydrogens on it. So again, that acid is being secreted out into the urine in that form. So we have different forms here, different players, but the take-home message is the same. The end game is to have hydrogen ions secreted into the urine and bicarbonate reabsorbed into the blood. Okay, glutamine is one of those molecules that in its metabolism, it helps in this process. It helps to buffer in that way. All right, we come to this Henderson-Hasselbalch equation. And this equation basically is a way for us to estimate the pH if we have the ratio of the bicarbonate and the amount of acid, the amount of carbon dioxide. So we can use this formula, which is 6.1 plus the log of the concentration of bicarbonate divided by the concentration of CO2. And if we use this equation in the reverse, we can determine the ratios of CO2 if we have a steady pH. So in the case of the body, where do we want the pH to be? Where do we say we want that window of that pH to be? 7.35 to 7.45. So for a pH of about 7.4, which is what we want, we know that we need to have a ratio of 20 bicarb to 1 CO2. Okay, and that tells us something very important. Anything greater than that ratio is going to be acidosis. Anything less than that ratio is going to be alkalosis. Right, so I'll say that again. The Henderson-Hasselbalch equation is an estimation of the pH given the concentration of bicarbonate and the concentration of CO2. So if we use this equation in the reverse, meaning that we want a set pH, and we use that set pH to determine how much acid and base we should have, we can say for a pH of 7.4, we need to have a ratio of 20:1 for acid to base, or sorry, for base to acid, okay? And that tells us that 20:1 is sort of our neutral ground. Anything above that 20:1 is going to be alkalosis. Anything lower than that 20:1 is going to be acidosis. Okay? And again, the kidneys and the lungs are going to help regulate any disturbance in this way. The kidneys will regulate the amount of bicarb and hydrogen, and the lungs will regulate the amount of CO2. Any questions so far? All right, let's move to the respiratory system. Let's talk about the respiratory acidosis. So again, the cause here is going to be hypoventilation. And this can be seen if there's, for any reason, there's some drugs that decrease your respiratory rate. If you're in a coma, you have a decreased respiratory rate. And so decreased ventilation means that you're holding on to CO2. And if you're holding on to CO2, what type of disturbance is this? Acidotic, right? So because it's starting in the lungs and because you're holding on to excess CO2, this is called a respiratory acidosis. So where's the compensation going to be? No, so it's starting in the lungs, so where's the compensation going to be? So what did we say about a disturbance that starts in the lungs? Compensation has to be where? In the kidneys. Right, the compensation has to be in the renal system. And the vice and the opposite is true. If you have a disturbance that starts in the kidneys, the compensation is in the lungs. So you start with an acidosis, which is because of hypoventilation. And so the kidneys are going to kick in. What are they going to do? And why? What are the kidneys going to do if you're holding on to CO2 because you're not breathing fast enough? What are the kidneys going to do? What do the kidneys do with excess acid? Secrete it. Secrete out those hydrogen ions. So now we increase the rate of hydrogen ion secretion. What parts of the tubule? What parts of the tubule are we secreting hydrogen ions? The proximal tubule, the distal collecting tube, and the collecting duct. Okay, what is the second thing we're going to want to do if we're holding on to excess acid? What's the second thing you're going to want to do if you're holding on to excess acid? Reabsorb bicarbonate, right? You're holding on to excess acid in the blood. You either increase the rate of secretion of hydrogen ion, like losing some of that acid, or you increase the rate of bicarbonate reabsorption. Okay, let's talk about respiratory alkalosis. So we talked about this quite a bit as an example. But respiratory alkalosis can be brought about by hyperventilation. Think about an asthma patient, think about a panic attack, think about someone who's being chased, right? Or someone who's not in the best physical fitness or physical shape. And so you have that hyperventilation, which you're losing excess CO2, you create a state of alkalosis. Decrease CO2 in the blood. Where are we going to see that compensation? We have an acid-base disturbance that's starting in the lungs. Where are we going to see that compensation? In the kidneys. What are the kidneys going to try to do to fix this? Decrease the hydrogen ion secretion. Right? We don't want to lose acid. If you're in alkalosis, we do not want to lose